questions, and she can prove them to you in real time, which is also the subject of her talk.
Thanks. That was a very awesome introduction. It just basically summarizes my talk. So ask me questions. No, just kidding. OK, so it's really a pleasure to be here and share my thoughts about delegated quantum computation. So this is the generic scenario we're looking at. We have a party here we'll call a client. It has an input row and wants to evaluate a quantum channel on the input row. And this will be done via an interactive process with a server, in general a quantum server, and will allow multiple rounds of interaction. So right off the bat, there's some trivial solutions that we'll want to eliminate in order to focus our discussion on something meaningful. The first solution is that the client does the computation herself. So she actually has a full quantum computer, or she's able to evaluate this particular quantum map, and she doesn't actually need the server. So we will eliminate this by limiting the computational power of the client. One extreme limit, as we've discussed already this morning, is having the client completely classical, or maybe we'll have some intermediate conditions that will apply on the client just to maybe limit the quantum operations that she can perform. And this will be a requirement, otherwise the discussion is kind of trivial, so we're always going to have some sort of limitation on the client. Secondly, we have a bit more of a cryptographic flavor of something that could be going on. So what if the server just outputs garbage? So maybe the server could be deviating from the protocol, or maybe the honest protocol says output garbage, don't actually evaluate the channel. So we want to eliminate this possibility also, and one way of doing that is to require some verifiability of the result, so that the client, even though she can't perform this quantum map, has a way to verify that the output is correct. A related concept has to do with privacy. So a trivial protocol in this context would be that the client just sends her input to the server in the clear. So she takes row and sends it to the server does the quantum map and returns it. That could be fine, but it's kind of trivial. In order to eliminate this possibility, we'll enforce a privacy constraint. So somehow the server should learn nothing, we'll formalize that later, from the interaction with the client. And this also touches on computing on encrypted data, so that we could see that this input row would be encrypted before sending it over to the client, to the server. And 2 and 3 are related. For now, we'll just say that we'll pick one of these conditions in order to focus the discussion. All known protocols that implement verifiability of the result, so there are known protocols to do these things, by the way. I'll tell you about them later. All known protocols that provide verifiability also happen to provide privacy. And this is not a coincidence, I don't think so at least, because we know that in the case of delegating the identity function, so just authentication, we know that verifiability implies privacy. But there are protocols that provide privacy only. And just a little note that will, most of the time, will require that both parties run in polynomial time. So both parties are efficient. This talk will be separated into two parts. The first part is about an overview, applications of delegated quantum computation, perspectives, open questions. And then the second part will get more technical of methods to perform delegated quantum computation. So the first application is, well, the delegated quantum computation. So just, there's nothing, it's exactly what we've defined so far. Here I have a picture where, to use one of the modern buzzwords, we have some cloud quantum computer, and we have these remote clients wanting to perform quantum computations. So this is really relevant, and given the current technological difficulty in building quantum computers, we can imagine that when they are available, they might be scarce, and they might also be remotely accessible. So maybe they'll allow clients to query them and perform computations for these clients. So with delegated quantum computation, the clients could delegate these computations while while keeping their privacy and while also ensuring a verifiability so that they can check that the computation is correct. This will be specific methods to do this will be the focus of the second part of this talk, so I'm not going to go into naming particular papers that do this, et cetera, at this point. Okay, second application would be proofs and interactive proofs, which we've already encountered this morning. From my biased point of view, much of complexity theory is about delegating computations, right? So if you have NP, for instance, it's the set of decision problems for which the yes instances have efficiently verifiable proofs. So the delegation here is that the witness is found. It can be found by a remote resource. In this case, it would have to, or in the most general case, would be infinitely powerful. But the remote resource, the server, would generate the witness, and then the witness can be efficiently verified by the client. So this is also generalized when we talk about interactive proofs, which is an interactive process of verification. QPIP, as we've already seen, is this class of problems. In this case, we'll limit the server to be a quantum polynomial time, and we'll ask for an interactive proof between an almost classical verifier and an efficient quantum prover. So the first implication is pretty obvious. If you have a delegated quantum computation protocol, then you have a quantum prover interactive proof with the same parameters. So depending on the power that you've given the client, the same power will be required here in the QPIP interactive proof. However, the other implication isn't clear, or at least I'm pretty sure it doesn't hold. So a delegated quantum computation works on quantum information. So for instance, if you want to verify a quantum coin, this is a fundamentally quantum problem, and you need to be able to process the quantum information in a delegated way. And QPIP works on classical decision problems. So you don't get the implication in the other direction. And the open problem that we've already discussed is, would every problem in BQP admit a quantum prover interactive proof with a fully classical verifier? So again, this would be that a mere mortal like me would be able to interact with a quantum server and be convinced of this decision problem. And there are known solutions, but they always kind of find a workaround. And the workaround, first of all, is to use an almost classical verifier. So for instance, a verifier that can process and communicate a constant number of qubits, or to use a classical verifier, but use multiple quantum provers that are assumed to not communicate. So in the case of multiple provers, it's really neat. You can kind of cross-interrogate them. So use the fact that they can't communicate to improve the power of your verification mechanism. So continuing with interactive proofs and the relationship with delegated quantum computation, another application is to dequantize a proof system. So dequantizing means like removing the quantum from a proof system. And this has been done in the context of quantum multi-prover interactive proof. So there's this class QMIP, which is a fully quantum class. So both parties, the verifier and the provers, the multiple provers, are all quantum. And it's been shown that actually it's not necessary to have a quantum verifier in this case. We can assume that the verifier is classical and that all messages exchanged are classical. And that leaves us with the class MIP star, which is multi-prover interactive proofs, where the provers share entanglement. So that's the quantum portion that's left in that interactive proof. And in order to prove this result, the method is to go through a protocol for delegated quantum computation. So the verifier, which initially is quantum, can delegate all its quantum power to one or multiple, or to a multiple number of the provers in this interactive proof. Therefore, we get that you can remove the quantum power for the verifier. And the significance of this is that it simplifies the landscape. So in complexity theory, there's like a lot of complexity classes, and the main question is, are they equal, or what's the relationship between the classes? And proving that two classes are equal just simplifies everything and makes life hopefully a little bit easier. And maybe only remotely related is a current big open question that I'm sure we'll hear more about this afternoon. And is it this afternoon, Tama, that you're giving your talk? I think so, yes. And we'll hear a lot more about this, certainly. Is the relationship between the class MIP, which is multi-prover interactive proofs, just purely classical, and MIP star, which is multi-prover interactive proofs with entanglement. So the open question is, does entanglement have any positive use in the context of these interactive proofs? So it's been shown recently that MIP is contained in MIP star, and this question is about the other direction. Are they equal, or are they different? And I don't know, maybe just thinking about this equality might help in solving this. Okay, continuing again with interactive proofs, so there's really a lot of relationship between delegated and interactive proofs, is what maybe the main, one of the big open questions that kind of links pretty much all the talks given during this entire semester is the quantum PCP conjecture. Again, from my biased point of view, I see it as delegation to the extreme. So there's many embodiments of the PCP conjecture, and they are very well exposed in the survey paper. That's already been mentioned, I think. And the one that I want to highlight is the quantum PCP version that has an interactive proof flavor. So it says that for any language in QMA, so QMA is kind of the quantum analog of NP, there exists a polynomial time quantum verifier which acts on the classical input string, as well as this witness psi. So this usually comes from the prover, of course. As well as a quantum state of polynomial number of qubits, such that the verifier acts as only a constant number of qubits from the witness and decides acceptance. So the reason I say this is delegation to the extreme is that the prover here, the verifier, is really computationally weak. It only accesses a really small portion of the proof and is still able to decide. Okay, another application, verifying quantum mechanics. Again, this has been kind of touched on already, but to go maybe a little bit more detail, given a black box or a quantum system that you've purchased, or maybe your friend claims that they're quantum or something, how can you know that this is true? How can you know that this is a quantum system? And in particular, the big problem is we can't predict the output of a quantum computation in the most general case, because we're just polynomially bounded classical people here. And this touches the scientific method that of predict and verify seems not to apply anymore in the quantum regime. But there's hope. And here's a little example. Consider factoring. So somebody might build a large quantum system that can factor the product of large primes. Well, there's an efficient method to verify the solution, right? Maybe we can't predict ahead of time what the solution will be, but once the solution is given, then it's easy to multiply the two claimed factors and to see if that gives me the initial input. So in this case, we did not predict the outcome, but we predicted the outcome of a verification process on the output. So it's almost like the scientific method.
Sorry, can you explain why can't you predict? I mean, if you sample two primes, you multiply them.
Oh,
then
okay,
you
yes.
can also predict.
So if I had sampled the two primes ahead of time, multiplied them, given that to the quantum computer, thanks, yes. So that in that case, I chose the primes to start with, so I can predict them. But if I had initially just chosen a random number, if I don't know ahead of time.
Yeah, it's not clear why that's important for scientific.
Yeah, it's true. There's definitely a workaround in this case. Yeah. But there's also a method to verify that would be different from choosing ahead of time the integers and multiplying them and then checking. Sure. I already said this before. Okay. Quantum proof or interactive proofs, which we've seen previously, they give a bit of a bootstrapping method in order to verify quantum dynamics. So that is that if the experimentalist is satisfied that she can completely characterize, control, that she knows exactly what a small quantum system is, for instance, 3 qubits, then she can run an interactive process with a remote, for the experiment, in order to convince herself that she controls the entire quantum system. And I actually looked up what a bootstrap was, and I thought it was kind of cool that it's these straps on cowboy boots. Okay. Another application, you may have this in the back of your mind, kind of wondering what's the relationship with a cryptographic primitive that's had a lot of attention recently, a quantum fully homomorphic encryption. So this was a big open question. It was open for about 30 years, and Gentry gave the first solution in 2009. So it's related to delegated computations because it has to do with computing on encrypted data. So a fully homomorphic encryption scheme is a public key encryption scheme that also has an evaluation algorithm. So basically the evaluation algorithm uses the public key and is able to evaluate a circuit, or a function f, on ciphertexts such that if you were to decrypt using the secret key the result of the evaluation function, you would get the function evaluated on the corresponding clear texts. So homomorphic encryption gives a way of delegating computations that are private. You can just encrypt your data using the public key, send it over to the server, server performs eval, and then the client can perform the decryption and get the output of the computation. And we require this compactness requirement in order to eliminate trivial solutions. So the compactness says that the length of the output of eval should be independent of the function itself. An open question is there a quantum equivalent to homomorphic encryption, to fully homomorphic encryption? There are known solutions for quantum computing on encrypted data, but they don't satisfy exactly a quantum equivalent of this definition, in the sense that it's important that the client's work should be independent of the size of the circuit, and that's not the case in currently known protocols. And I think that in order to answer this question, we're going to need new fundamental insights on computing on quantum data and computing on encrypted quantum data. Okay, another application of delegated quantum computations is device independence. So in device independence, what happens is that a party has think of it as a party has purchased some computational devices from an adversarial party. So they don't trust that the purchase that they've made actually follows what the seller claims it follows. So for instance, if you're trying to do quantum key distribution with some devices that you bought from a specific company, how do you know that there's not a side channel that outputs the key to some third party? Well, using device independence, it's possible to implement these functionalities without having to trust the devices themselves. And we only rely on the assumption that devices are separated and they don't communicate. So again, it's a bit of this cross-interrogation process that allows us to gain certainty on the level of security that we want. And actually, I'll go back. So it's been shown that delegated quantum computation gives us device-independent quantum key distribution. So it's actually kind of, if you can delegate quantum computations with a classical client and quantum servers and be convinced of the answer, then you can have the quantum servers measure half EPR pairs. And that gives you a key that is secret. So it's actually kind of like complicated way. So delegating computations is it's difficult in general, very general task. And then if you limit it to measuring EPR pairs, then you get device-independent quantum key distribution. And an open question is, what else can we kind of rephrase in terms of delegated quantum computation? Although we have ways of doing device-independent QKD that's even feasible and fault-tolerant, et cetera, can we rephrase that in terms of delegated quantum computation, or the other way around? Could delegated quantum computation give us new insights into this device-independent cryptographic task? And are there other cryptographic primitives that could benefit from relationships with device independence? Okay, so yet another application, one-time programs. A one-time program can be seen as the following. So a sender and receiver have a joint quantum input, as well as the sender knows of a quantum channel that she wants to encode into a black box. So via a quantum process, she does that, and then she's able to send the black box to the receiver, who at a later time can evaluate the channel on this joint input row, get the output, and then the box self-destructs. So it's one time in the sense that you can evaluate this channel only once. And this was shown to be possible in the model where we allowed quantum information as well as classical one-time memories. So this is a bit different from delegating computations, because in this case, this party here, the receiver, which takes the role of the server, actually now provides an input and receives an output. So in the delegated case, it was the client that provides the input and gets the output. So we needed to develop new techniques to deal with this, but it is a form of delegating computations.
Sorry, can you give a sense of why one would want to do that?
Why would want to do quantum one-time programs? Oh, so one-time programs would be useful for digital rights management. So maybe you buy a product and you can use it once. Coins, things that that you want them to expire after single use. And this is a very general scenario. It's like running a quantum circuit, but maybe you have more specific circuits that you want to do.
Is it important that a state is shared between the sender and receiver?
So this picture is the most general case again. So that they have this joint input row and they want to evaluate this channel on A and B. It's just the most general possible way. I actually kind of admit that in my previous pictures were not the most general, but I meant them to be this actually. Okay, so a related open question related to runtime programs in the sense that we're looking for a functionality where the receiver provides an input and gets the output is called program obfuscation. Yeah?
So I can ask about the one-time program again. Let's suppose that the sender and receiver did not have an entangled input. So the sender, Microsoft wants to make a bunch of software programs that the receiver can evaluate on their own thing, and they want to package it up. Then the package, is it correct to say the package would include a quantum state together with a classical one-time memory? And you could just sort of put that in the mail and then, not interact anymore, and the receiver would use it?
Yes. Okay. Yes. For the benefit of others, the question was, if there's no joint, if I understood correctly, if this isn't a joint entangled state, what would the one-time program look like? So, remove this, and there's maybe just an input, or maybe not even an input, maybe just a channel that you want to hide. And then in that case, the one-time program would look like quantum states as well as classical one-time memories, which are actually modeled after 192 OTs. Oblivious transfers. Okay, so open problem is quantum program obfuscation. So quantum program obfuscation would allow a receiver, similarly, to evaluate a channel where the receiver doesn't know the channel, so the channel would kind of be hidden, but it doesn't have this one-time property. So it's more like it could be possible to run multiple times, but it should not be possible to extract too much information about this quantum channel phi. So there's multiple definitions for program obfuscation, but one that was used in a classical impossibility proof by Barat, Goldreich, and all these other authors. So they have this impossibility proof saying it's actually not possible to do program obfuscation. The proof doesn't hold in the quantum case because of the no-cloning theorem. So they have this little part of this proof that they kind of assume that they can copy information. Well, that's not the case for quantum states. So it's an open problem whether we could do program obfuscation. This is the end of the first part of my talk that talks about general overview applications. So it's a good time to kind of pause for questions if anybody is wondering. Yeah.
So you can go back one slide. So
One slide.
about the program obfuscation. So I think recently there have been some positive results classically about this.
Yeah. Yeah.
So,
So how does that relate to this?
Yeah.
So the recent positive results on classical program obfuscation had to do with using a different security definition. So it's called indistinguishability obfuscation.
Yeah.
So they showed that it was possible. So so it doesn't contradict this impossibility. It just has to do with
but
definitions.
and actually, I'm just wondering, what's your definition of the quantum program obfuscation? So do you change the whole model or just change part of it?
So what's the definition of the quantum program obfuscation that we'd be looking for here? Well, in order to make it the most interesting result, we could try to use the definition that was used in the impossibility result, which was a simulation-based definition. So we could take a quantum version of that and then try to show that that would be possible.
Okay. I can't remember another result. Maybe I'm wrong. I think there's some result by Jordan and some other authors about some negative result on quantum program obfuscation.
Stacy was on that paper, I think, and negative result on.
Not a negative result.
No.
We had a proposal for a quantum obfuscation, but there's not really anything rigorous to say. So really
So I think it was, if I can kind of summarize, it was using some intermediate security definition with heuristic proofs.
Yeah, I never used heuristic, so.
Yeah, it was heuristic, so it wouldn't kind of necessarily fit into this mold right away. Yeah, another question?
I'm not very familiar with this. What is just classical program obfuscation, and how is that different from something like homomorphic encryption?
What's classical program obfuscation, and how is that different from fully homomorphic encryption? Can I have another hour? Well, okay. Program obfuscation.
By the way, you also have markers there if you want to use them. Just
Okay,
so
yeah,
you
thanks,
can-
thanks. Oh, this is a whiteboard.
Yeah.
Too. Okay. Okay, so I think of program obfuscation as a way to hide the source code of your program. So maybe you've developed this cool new Java applet and you don't want people to know how it actually runs, but you want them to be able to run it. Okay. And fully homomorphic encryption is that you want to benefit from remote resources that can do computations for you, but you don't want to reveal the data. So you want to encrypt it before sending it over to the server. So they both have a flavor of delegation. This one is a bit more far-fetched than the other one.
So
And
it's
one of
data encrypted versus program is encrypted.
Well, that makes it sound really trivial because there's via universal circuits you can kind of get from one to the other. It's also fundamentally that the receiver in obfuscation provides input and gets output. In fully homomorphic encryption, it's the sender or the client that provides input and gets output. So I think that's easier. It's a lot easier than to deal with the cheating party provides the input and gets the output. It gets harder. Okay. Any other further questions about applications and stuff like that? If not, we're going to move on to specific methods to delegate quantum computations. And I have 3 in mind. We'll see how far we can get. And and they're kind of an increasing level of difficulty, perhaps, especially with regards to the first one is quantum computing on encrypted data, so we just want to have privacy. The second one, quantum computing on authenticated data, so we want to have verifiability. And the third one is, well, now we really want a fully classical client. In order to do this, we can, if we postulate multiple servers, we can do it. So how to do that? Quantum computing on encrypted data actually has a relatively long history, starting 2005. So now we'll imagine that the client, before sending her data to the server, encrypts it with some sort of key K. And then there's interaction. Perhaps the key needs to be updated to K prime, and the client knows what that key K prime is. And at the end, she can decrypt it and get the result of the computation. And they're, depending on if you use the child's result or a more recent result called quantum computing on encrypted data. So this was a joint theory and experimental paper. So the child's result requires more resources from the client point of view. And then we've reduced this to sending random BB84 qubits. And I'll show you how. So I kind of suppose that everybody's familiar with universal gate set. So the channel we'll assume that we have a circuit description of the channel using this gate set with Pauli's, Clifford, and then this pi over 8 gate, or R, will be the non-Clifford group gate. And then we'll use this decomposition in the protocol itself. We'll also use an encryption scheme, and the most obvious encryption scheme, if you want information theoretic or statistical security, will be the one-time pad. And in the quantum case, the quantum one-time pad involves randomizing the quantum state with a random Pauli operator, so a random X and a random Z. So the key has two classical bits, A and B. And here is a high-level description of the protocol. You should kind of imagine what's going on, that the client has an input row, and she starts by encrypting it with these random Paulis. And then these red exponents are the actual key. And then she sends her data to the server, and will write on each wire the corresponding key, such that if she were to decrypt these wires, she would get the data at that point in the computation. And then there's going to be little gadgets, kind of sub-protocols for each of these potential circuit components. So for instance, we want to do an R gate, well, we go into this sub-protocol. And at the end of the sub-protocol, the client has updated her knowledge of the key so far, and et cetera. We have 2-qubit gates, slightly more complicated, and we'll just keep on going. Whoops. At the end, the server returns the output to the client, who can decrypt the output and get the result of the computation. And well, for the client to prepare single qubits and to do measurements is relatively easy. So this one, she just sets the key to be 0. And if you want to do a computational basis measurement, then the B key, so the exponent of the Z encryption, doesn't matter at all. So you can just throw that out. And then when you get a classical bit out of the measurement result, all you have to use to decrypt it would be the classical key for the X Pauli matrix. And it's not that hard to do all these Clifford group gates on encrypted data. So actually, this is by definition. The Clifford group is a set of operators that conjugate Pauli operators into Pauli operators. So there's always a key update rule if you apply a Clifford group gate. Okay, they get slightly more complicated here, but it's possible. So the only problem you run into is when you want to do a non-Clifford group gate on the encrypted data. And what happens if you work it out is if you do this pi over 8 gate on encrypted data, you get this key update rule that includes a P. This is a phase gate, and this is not, you don't want this. So how do you get rid of that? Well, Childs has this idea that let's use quantum interaction in order to get the server to undo this P gate. So here's what happens. The data wire is encrypted here. The server does the R gate with the potential P error, sends it back to the client who decrypts it, and then she's going to either send the server a dummy qubit or send him the real qubit, depending on whether or not P should be applied or not. But the server's not going to find out because the qubit will be encrypted. He always does P no matter what and returns it, and then the client can decrypt it. So this requires, from the client point of view, to be able to do a swap gate as well as quantum interaction in order to exchange this quantum register. And the question was, well, is this really necessary? Is this quantum interaction required? And the answer is no. So in recent results, it was shown that the server can be led to correct this error, this P error, using an auxiliary qubit that's independent of the computation, as well as classical interaction only. And this can be done via the circuit here, which looks a bit daunting. It's inspired by kind of gate teleportation and the circuit manipulation techniques. And, well, yeah, people are kind of falling asleep, so I think I'll just kind of skip this quickly and say that what goes on is we use this auxiliary qubit, we use this classical data, and the net effect is that the server applies this correction if and only if it had to. And there's classical communication in the sense of returning this classical bit. And this is the key update rule that the client needs to take into account. Okay, security. So it's relevant, yeah.
You presented, as far as I understood, you presented that there was this issue that you'd have this extra P that you couldn't sort of update, or you couldn't somehow decrypt. Is that?
The extra P doesn't fit into it's not a key. It's just this extra error that we need to get rid of because it doesn't. We want them to be only poly operations, so just encryptions.
Right. So without necessarily going into detail, what's the main idea for how you managed to do that?
Okay, yeah. In this circuit, well,
Yeah.
what the main idea of how I managed to do this, and thanks for kind of letting me focus on what I wanted to say here, is that there's an auxiliary qubit that is sent by the client to the server that has a hidden P in it. So this is random. It's a hidden P, and then it's encrypted after that. And this randomness is sufficient such that the server will do a P correction, but it'll be a random from his point of view. He doesn't know if it's a meaningful correction or if it's just kind of undoing this random one here. And he does this P conditioned on a classical bit X that he receives from the client. So everything is kind of works together, the quantum auxiliary qubit and the classical bit, such that he'll be undoing the P only if he needed to, but he's not going to find out if A was equal to 1 or 0. Does that kind of help a bit? Okay, security. So it's intuitively clear. So we're using encrypted data. So it should be secure, right? But there's interaction in this protocol. So how do you define security? How do you say, well, that, what are you trying to prove, and then how do you prove it? And how do you formalize it? The server learns nothing via this interaction. This is done via techniques established in modern cryptography, which generally have to do with simulation-based security definitions. So we look at the real protocol here, which is the interaction between the client and the server, and consider S prime being any deviating server. And then we look at this ideal world, which has to do with a simulator. So the simulator depends on the deviating server that you've chosen, but note that the simulator here doesn't interact. It doesn't get the client's input. It only gets the same input that the server gets in this world here. And if for every possibly cheating server there exists such a simulator, such that these two channels are indistinguishable, then we'll say that the original protocol was secure.
Sorry, can you try that one more time?
Yeah, try that one more time. Okay. So you look at the actual protocol and what's going on in the actual protocol. Let S prime be any deviating server. So try to think about this as the most malicious server you could come up with. And it has an output here, right? So it might be able to extract information about the private, about the client's private data and output it here. That would be bad. That would be very bad. This ideal world here is secure by definition. It is a simulator or whatever, a party, just a map, that doesn't have access to the client's input. So how could it possibly cheat? It can't. It just gets the input of the server. It doesn't have no communication whatsoever. So this has to be secure by definition. It's just a map that takes its input and outputs something. So if for every possible cheating server here, there exists a simulator such that these two maps are indistinguishable, this one is secure by definition. So if it's indistinguishable from this one, well, then this one must have been secure to start with. Yeah, Aaron?
And there's for row in, is that sort of for all possible
Yes.
row in?
Yes, for all possible row in, because I'm talking about maps.
Okay.
So it is for yes.
So you could also just say that phi has no dependence on the C part of the input.
Maybe.
But okay, yeah.
Yeah, so that would be again, an intuitive way of doing. I don't know how to formalize that,
I
but
see.
that indeed you want to show that this map has this output at least has no dependence on this part of the input. Yeah. And there's interaction in this protocol too, so it gets complicated.
So that's computational indistinguishability, or?
Oh, thanks. So this is a general picture, but we're working with statistical, so statistical indistinguishability. But it could be applicable if you're looking for a computationally secure protocol. So in the statistical indistinguishability for quantum maps, it's called diamond norm. Yeah.
In this protocol, how do the resources of the client compare to the resources of that's required by the server?
In the protocol, the resources of the client that we've looked at, the best one that we know of, the client has to generate these auxiliary qubits, which are a unitary equivalent to BB84 states, so plus, minus, 0, and 1. And the server has a full quantum computer. And the server client also has classical computation.
Do you have one of these BB84 states for every R?
Yes, exactly. Yeah, one auxiliary state for every R state, for every R gate. So, so this is the security definition. The proof, I'm just going to say that there's a very nice proof technique to take the original protocol, convert it to a protocol that uses entanglement. So we don't want entanglement in the final protocol because that's complicated. But as a proof technique, we'll convert it to a protocol that uses entanglement. And that protocol will be trivially secure. So then you can argue indistinguishability between the various protocols and then go back to the original protocol and say that it was secure.
Sorry, so having used that as the proof technique, is that really how you see it, or do you now that it's all put together, do you see it in some other way?
So I see encrypted qubits as half EPR pairs. That's that proof technique has kind of changed my way of viewing encrypted data, but that's about it.
Sorry, so you see encrypted qubits as half EPR?
Yeah.
Okay.
Yeah. This line of work is related to what's called blind quantum computing that historically came between the Childs protocol and the one that we've just talked about. The main purpose was to hide the computation being performed, but as I already mentioned, there's a easy translation between using universal circuits between hiding the computation itself and hiding the data. This blind quantum computing was developed in the measurement-based model for quantum computation. It requires a little bit more quantum resources from the client. It needs to be able to prepare random qubits chosen from a set of 8 possible qubits. And there's been a lot of follow-up work on blind quantum computing, and this is just a sample of it. like a written up summary of where things
just
stand?
a two-sentence summary.
I don't know. I don't really know what to say. A summary on where things stand. You know, there's been work on what's the power required of the client. There's one like with measurement where Alice only needs to be able to measure qubits. There's different results on, did I even include it here? No. On composability, the composable security of this protocol. There's experimental demonstrations. So I don't think I can summarize this in just a few, just one phrase. Yeah. So the next protocol I want to talk about is verifiability, and it can be seen as adding an extra layer of encoding in order to be able to verify the computation. So very much related to the previous one, but let's just like make the encoding not just an encryption, but something a bit more complicated in order to provide a verification mechanism. And again, the client wants to be able to verify even though she can't do the computation herself. So this is kind of neat. Okay. So the main idea is tamper-proof computation. The client is going to send an encoding of the input, and the auxiliary qubits are also going to be encoded. The encoding is tamper-proof in the sense that any changes are detected, but it's malleable in the sense that the server should be able to perform gates on the encoding. Okay, and the encoding itself will be what's called quantum authentication codes. And you should think about this as an error detecting code that catches almost all errors. Necessarily, there's going to be a key, because this is a cryptographic scenario, so the key is going to kind of hide which errors are not going to be caught. And then, in order to perform gates on the tamper-proof encoding, we're going to use a method called quantum computing on authenticated data. You should think about this as an analog to fault-tolerant quantum computing, but on data that's been encoded with a tamper-proof encoding. QCAD is going to require auxiliary qubits that the client is going to prepare, as well as classical interaction between the client and the server. And QCAD was used for the first time in the context of quantum multi-party computation. Okay, we're going to use as an authentication code something called encode and encrypt. So we're going to encode the data and then encrypt it using a random poly. The advantage of this is that the random poly actually breaks down the attack into a convex combination of poly attacks. So all we have to do is deal with poly attacks. So I'm not going to go into details of this, but we've developed like this simpler authentication code, I think anyways, that we call the trap code. So you take the data, you encode it into an error detecting code, then you append these auxiliary qubits that are traps, zeros or pluses, and then apply a random permutation. And the key is the random permutation itself. And so it's kind of intuitively clear that this is an authentication code. Now, to check it, you just apply the inverse of the permutation, and then you measure these traps in their respective basis, and if they all accept, then you accept. And then now we need a method to perform gates on this data. And this is done using gadgets, kind of like what we saw in the previous protocol. And, well, yeah, I'll just say that these gadgets require some interaction and also auxiliary qubits. And they're kind of inspired by fault-tolerant quantum computing and gate teleportation. So the protocol for quantum computing on authenticated data is that the client authenticates her data and the auxiliary qubits, sends them, then there's interaction to execute these gadgets. And now we have the same problem, like how do you define security and how do you prove security? And the most general security definition that makes this protocol as useful as possible is called a composable security definition, or universally composable. And this is what has been done. So, and this also postulates a real world and ideal world and shows that these two are indistinguishable. And I also just want to mention that, intuitively security is clear because you're computing on authenticated data. So it should be verifiable. But then again, there's interaction. And how do you fit that into the security proof? Well, this is actually shown to be totally non-trivial. I'll just stop there for that. The next delegated quantum computation that I want to mention is you want the client to be totally classical. And we'll do this with 2 provers, because we don't know how to do it with only 1 prover. And this has been done using very different techniques, although certainly they're related, but how they're related exactly is still an open question. So the CHSH game. So this is the game. A verifier, here that's E, well, a verifier provides questions to Alice and Bob, and they need to provide, these are just bits, and they need to provide answer bits such that the XOR of the outputs should equal to the multiplication or the AND of the inputs. And it's really well known in quantum information that quantum devices can win this game more often than classical devices. So they can win about 85% of the time. Classical devices can win at most 75% of the time. And the strategy is to use a shared EPR pair. So this is a very rudimentary test of quantumness. You do the CHSH game. And the question is, can we scale this up? I just realized I'm missing the reference here. Oh, the reference was on the previous slide here. Okay, the question is, can we scale this up in order to characterize larger quantum systems or further quantum operations? And the answer is yes. So if we do a sequence of n CHSH games, and you observe that the servers win close to the optimal fraction of the games, then the theorem says that they must have been acting according to something close to tensor product of the ideal strategies. So this is very powerful because it gives you a way to characterize the quantum actions of these servers. So what's been done is that in order to take this and make it into verifiable delegated quantum computation, you combine various subprotocols. So either the players or the provers are doing a CHSH game, or they're doing something called state tomography, which kind of characterizes the system that they're operating on, or they're doing process tomography, which characterizes the channels that they're executing, or they're doing the actual computation that you want them to do via a gate teleportation type of technique. So there's these 4 scenarios, and the point is that from this party's point of view, these 2 scenarios are the same, and these 2 are the same. It's the same operations that the verifier will ask them to do. And for the other party, these 2 are the same, and these 2 are the same. So they're forced to behave identically in these indistinguishable protocols, and we can use that to, you confirm here the state, their entanglement, the state, the process, and you use this information to gain confidence on the fact that the portion that's doing the computation is doing the computation correctly. Okay, so this is the end of my talk. Usually I would kind of talk about open questions and give a perspective, but that was the entire first part of the talk. So instead I'll just give this table that summarizes the 3 protocols that we've talked about for computing on encrypted, authenticated data, or the rigidity of the CHSH game protocol. Thanks.
We have time for some questions.
Yeah, computing on encrypted data, you said it was like a theory experimental paper.
Yeah.
What were some of the experimental results?
So the quantum computing on encrypted data was a theory and experimental paper. And the theory was the protocol, the proof, and all that. And what was the experimental results? Well, it was that we were able to build it. So they were using optics, and it was possible to implement the basic gate set with a reasonable fidelity. So the big challenge was to do this R gate, this non-Clifford group gate, and that required 2-qubit interactions and well, it was shown that it was still possible to do it. And it was the first time that was a relatively, there's always a divide between the experimental security and the theoretical security. But I would say it's the first time that there's a relatively reasonable level of security in the protocol, because there was this active switching of always changing the encryption between the runs of the experiment.
Who were the experimentalists?
Who were the experimentalists?
And so where were they?
So it was in IQC, University of Waterloo. I only wrote once the entire names because there's. So there was the first author is the graduate student, Kent Fisher, and it was in the lab of Kevin Rush. So Fisher, Broadbent, Shalm, Yan, Lavoie, Prevedel, Yenavine, and Rush. I don't know why it takes them 7 people to run this device. There were some technical problems.
So, just a vague question, what would be a ambitious but possibly realistic next result?
Ambitious but possibly realistic next result? I'm really excited about fully homomorphic encryption and program obfuscation.
And you believe they're both, your intuition is that they should both be doable?
Yeah. Yeah.
Actually, I have a similar question. So is there a master result, like saying that there is a protocol where like the server does not learn anything, the verifier can verify, the verifier can knows that what's going. So is there like an ultimate result that we can hope for, or there is no such thing?
Ultimate result you can hope for. I don't know, the multiple server with a classical client gets pretty close to that. It's fully classical, then multiple servers. Is it possible with only classical server? No for delegated computations, because the input could be quantum, so you kind of have to have something quantum. But maybe for classical computations, yeah. So the fully classical client and quantum polynomial time server, QPIP with a fully classical client. I think that's a big question.
So the server is always quantum, right?
Yes.
And the client is either quantum or classical.
Well, you want some sort of restriction on quantum.
But the client is classical, and but there is also the security aspect. So, for instance, in the last result, you explained there is absolutely no security aspect. You just want to verify that the servers do what they are supposed to do.
Well, that's a security aspect.
Yeah, but they can learn can learn your output, and they can.
Oh, yeah, I didn't mention that, but it so happens that it is also secure in the privacy realm. But the goal was verifiability. Yeah, classically you can have verifiability without privacy, but I think that quantumly that's not the case.
Ed?
Oh.
This is a question along the same lines, but for this open question about QPIP being equal to BQP, are there any proposed protocols that can't be proven secure, or is that no one even has an idea about how one would run?
Yes, so for a fully classical verifier and
Yeah.
a QPIP protocol, nothing's been proposed. I don't think it's true.
Okay.
I don't really see how you can do that, but the best you could hope for, I would say, would be the verifier having the capability of maybe any two non-orthogonal states. Maybe that would be optimal. But
Okay, so if there are no more questions, let's thank Anne again. And we'll start again after lunch at 1:30.